Hello and welcome to the section on factoring polynomials. Factoring is undoing. Now you remember way back we talked about the law of opposites. In chapter 2, even with a scriptural basis, there is an opposition in all things. And certainly the opposite of multiplying is dividing. But there's also this other way of undoing multiplication, which is factoring. I'll show you what I mean. So when you have multiplication like 5 times 12, you get the number 60. Yeah. Well, if you have one of the two factors like 5 or 6 or 12, you divide it into it and you undo that multiplication. But if you don't know them, you have to go through a process of actually figuring out, oh, what is it that times is up to 60? And you do something like this. Oh, it's 6 times 10. Or it could have been 5 times 12 or 4 times 15. And then you look at these numbers, and do they go down even further? Yeah, that goes down to a 2 and a 3, and that goes down to a 2 and a 5. And you're breaking up this number 60 into the numbers that the prime numbers that multiply to get them all the way up to 60. So here the factoring is undoing the multiplication that happened in any multiplication that brought it up to 60. We are taking it back down. So we're undoing multiplication. So when we think about factoring polynomials and how many different ways we could multiply them together, we're going to take the factoring of polynomials in 5 different chunks because there are so many different ways that it happened. So let's look at this. The first way we did multiplication with polynomials is that we distributed. We took something like 2x into x squared plus 5x minus 8. And we distributed it in. We got 2x cubed by adding the exponents plus 10x squared minus 16x. That was distribution. So if we're going to go backwards on that, we're going to see what is the greatest common factor of these three. And that was like, hey, somebody jumped in a 2 everywhere. And then an x is in everywhere as well. And then we pull that 2x out. So instead of jumping it in that direction, we're going to pull it out this direction and now have an x squared plus a 5x minus an 8. And you're like, well, that just, yeah, it went backwards. Here it was multiplication and there you did backwards. Exactly. So the thing that this goes backwards on is the distributive property. That's exactly what it undoes, is the distributive property. So let's do a couple more. Let's try this one. 9x squared plus 15x. Something, ooh, did somebody jump something in there? Yeah, what can go into a 9 and a 15? Well, a 3 can. Do we have x's in both places? Indeed, there's a 3x, and we get, let me see, 3x there and a 5 there. Does that work? If you were to distribute that back in, does it work? Indeed it does. Let's try a bigger one. How about 30x to the 4th y plus 18x cubed y squared minus 24x squared y cubed. Ooh, yuck, that's a huge one. Well, if we look at this, some of you might be able to say, hey, look, I can see a 3 in each of those. So you take a 3 out and you're like, I can see an x squared in everything. So you take a 3x squared out. Then you get 10x squared y plus 6x y squared minus 8 y cubed. Yeah, you pulled that x squared out. And notice once you pull them out, the exponents subtract, and when you're taking out all the x's, and you take it out. Well, is there something that can still come out of this? Yeah, there's a 2 that can go in 10, 6, and 8. And there are y's in each one of these. So you could pull out, in addition to that, a 2y coming out of here. So we have 3x squared and a 2y, which now leaves 5x squared plus 3xy minus 4y squared. And this out front is now a 6x squared y. 5x squared plus 3xy minus 4y squared. Excellent. Now notice, this is why we title it GCF. This method of unmultiplying polynomials is when you pull out the greatest common factor. So you have to find out things that are common to all of these and find the biggest one. Otherwise, you'll end up doing it 2 or 3 times. We could have done this from the very beginning and noticed, oh, in 30 and 18 and 24, there is a 6. And the number of x's that are in each one of them, there are at least 2 x's in everything. And there is at least 1 y. Here are a few more that we're going to do. 2x squared m plus 5m. What can you pull out of there? We can pull an m out, 2x plus 5. Notice that that's the same as if we were to pull it out to the right. We could write it as 2x plus 5 times m. You could distribute from the right or the left. Okay, let's do another one. 2x squared, oh, I forgot the squareds on those. 2x squared q plus 5q. Well, we pull out a q and we get q times 2x squared plus 5. How about 2x squared times Jim plus 5 Jim? Yeah, Jim is now in our problem. Let's just take him out. We could take him out to the left or the right. Take him out to the front. Jim, undistributed from that 2x squared plus 5. That's awesome. Okay, what about 2x squared times squiggle plus 5 squiggle? Assume those are the same squiggle. Well, we get a squiggle. Let's take it out to the right this time, just because we can, and squiggle. Good. Yeah, just like that. And you're like, what are you doing? Well, we get to do this with even bigger things. Look at 2x squared plus, say, m plus 8 plus 5 times m plus 8. Can you see that this guy and this guy, same thing, act just like Jim or the Q or the M? We can pull the whole m plus 8 out and get this, m plus 8 times 2x squared plus 5. Yeah, look at that. So this actually prepares us for our next one we can do, this pulling out this greatest common factor, especially when the greatest common factor is in and of itself a binomial, shows us how to do grouping. So let's move on and show you how to do grouping. We'll leave this guy up for just a moment. When we multiplied two binomials together, we would go like that, and we'd have 2x squared m, and then distribute again, plus 16x squared plus 5m plus 40. So the question becomes, how do we undo this? And that's what grouping is all about. When you have 4 terms, that means that you had a binomial times a binomial. If you pulled out all the greatest common factor you possibly can, but somebody actually did this special case where they actually used FOIL, that special case where you have front, out, inner, and last. So let's put it over on this side. 2x squared m plus 16x squared plus 5m plus 40, and see how we get to that. Well, notice how these are broken up into 2 pieces to get to there. This is what you're going to do with 4 terms. Chainsaw, cut this guy in half for just a moment. Group the first 2 terms and the last 2 terms together. This isn't factored, but is there a common factor you can pull out of these 2? You're like, well, yes, there's a 2x squared there. 2x squared. And we're left with m plus 8. And over here, we can pull a 5 out. 5. And what's left? M plus 8. And look at what we have. A binomial that is consistent in both halves. Glue them back together, and we have this one where we're like, oh, hey, look, we can now pull out the m plus 8. Let's pull it out to the right this time. 2x squared plus 5 times m plus 8. And we have done exactly backwards of FOIL. Isn't that amazing? Grouping, chops them right together. Let's try another one like that. Here's one, 10xa plus 15xb plus 14ya plus 21yb. And we have 4 terms, which means somebody did an FOIL, if it factors at all. So let's chop this guy in half, chainsaw. What can we pull out of the first 2 terms? It looks like there's a 5 and an x. So 5x, and it was left with a 2a there and a 3b on that one. What about this guy? Looks like a 7 can go into 14 and 21 and a y. So let's pull out a positive 7 and a y. And we're left with 2a plus 3b. Now, this is important. When you get to this point, if these two binomials, these two guys right here, don't match, then either you have made a mistake or this is not a factorable polynomial. And if it's not factorable, just like with numbers, we would call it prime. But they are the same. So let's pull this guy and this guy out. I'm going to pull it out this way. So we've got the 2a plus 3b, and we're left with a 5x and a 7y. And now check it out. If you were to multiply these two together, 5x times 2a is 10xa. 5x times 3b is 15xb. There's that guy right there. 7y times 2a is right there, 14ya. And then 7 times 3b is 21yb. All right, here's one more. 5x cubed minus 10x squared minus 3x plus c. How many terms does it have? It has 4. We first check, can we pull out any greatest common factor? That's the easiest one, the slickest one, and we'll get the numbers down. Is there anything that's 5? And there's a 5 there, but there's no 5s here. So no, there's nothing common amongst them. So let's go straight to it. Chainsaw. What can we pull out of the first half? Looks like a 5. And greatest common factor, an x squared. Good. So we're left with an x minus 2. Alrighty. What can we pull out of this? We can pull a 3 out. We'd be left with a negative x and a plus 2. These don't match, but they're kind of similar. Uh-oh. Is that a problem? Well, not really. Look at what we're trying to find. We've got to pull something out. If we're going to try to get as close to matching as we can, we've got to pull out that negative sign. So a good rule that you will be able to use is to pull out this sign as well, and it will help this guy to remain positive after you pull it out. So that guy's a negative. So then if we pull out the negative 3, this is now a positive x. And if you pull out a negative 3 from a positive 6, you now have a negative 2. Yeah, so look at that. Shazam, there's the x minus 2 and x minus 2 that can pull out. So we're left with the x minus 2 coming out on this side, and we're left with a 5x squared and a minus 3. Shazam! That is grouping. It's awesome. So we've now covered something that you can apply to all polynomials. See if you can pull out a greatest common factor. If there are 4 terms left, then you're able to undo FOIL. What if there are 3 terms and something happened? Well, let's look at the multiplication that caused some of those to happen. So something like x plus 3 times x plus 8 would have been x squared plus 8x plus 3x plus 24. And yeah, this did, with grouping, you could have undone that really well, but there was a combining that happened in here, and it gave you x squared plus 11x plus 24. So we have to undo this. So we can't go back and do grouping. We don't have the 4 terms. We don't know how to chop that guy up. So let's see if we can see the pattern that we need to undo. We notice that this guy is 3 times 8. Yeah, indeed. But 11, how does that connect up with a 3 and an 8? And you're like, wait a second. 3 plus 8 is 11. Let's see if that always works. X plus 5 times x plus 7. Multiply those two and you get x squared plus a 7x. I'll write it up really small. Plus a 5x. What do those combine to? Yeah, plus a 12x and plus a 35. So when we look at that polynomial, the 35 came from 7 times 5, and the 12 is 7 plus 5. Indeed, one more. X plus an 8 and x minus 2. If this is really the case, this pattern, then this should be x squared negative 2 plus 8 is a positive 6x. Yeah, plus 8x minus 2x is in the middle, minus 16. And indeed, that is the case if you multiply those out. So going backwards, we have to identify this pattern. What multiplies to this and adds to that? And that is what those two are in there. Now this is, you'll notice we've separated out. We're only dealing with leading coefficient 1 out here in the front, and this pattern will hold. All right, let's do some of them. So if we had something like x squared plus 10x plus 24. All right, let's see if we can do it. We know it's an x and an x, and then what times is up to 24? Let me write that over here, 24. Well, a 1 and a 24 could, a 2 and a 12, a 3 and an 8, or a 4 and a 6. Do any of those add to a positive 10? Indeed, a 4 and a 6 do, and plus 6. Excellent. So if we had something like x squared plus 11x plus 24, it would be a different set. We'd have an x and an x, and what times is to 24 but adds to 11? Oh, that's that one right there. Look at that. Plus 3 and plus 8. Good deal. Okay, let's try another one. X squared minus 2x minus 35. Now this is a little bit different. We've got some negatives to worry about. So they have to times the two numbers. Let's write out where we've got. So it's x and an x. And the two numbers that fit here must times up to a negative 35 and then add to a negative 2. So we could have a 1 and a 35 or a 5 and a 7. And we realize that it's these two numbers. Whereas over here they added to a positive 12, they've got to be opposite signs to multiply to a negative number. And so when they add, a negative 7 and a positive 5 are the ones that will add to a negative 2. Notice if you switch these ones around and have something like x minus 5 and x plus 7, you move the signs, then when this multiplies out, you get x squared plus 7x minus 5x. That's a positive 2x. That guy won't work. Let's try one more. X squared minus 10x minus 24. So we've got to find x and an x. Now I should note right now why we call this try fast. Every problem that we've done is one step. Sometimes we have to really think about what numbers go in there, but we are just looking for the numbers that follow that pattern. So in this negative 24, we do have to check our answers, but it will always be one step. Once we can find those numbers, we're done. So minus 24, so take it to a, let me see, could be a 1 and a 24, 2 and a 12, 3 and an 8, and a 4 and a 6. And many of you are thinking, oh, look, yeah, we did that up here. It's a 4 and a 6, add to 10. This is kind of a difficult one, or at least tricky, because if we've got to add to a negative 10. You're like, oh, that's easy. Negative 4 and negative 6. Okay, what's negative 4 plus negative 6? Negative 10. What's negative 4 times negative 6? Positive 24. Sorry, no dice on that one. These guys added to 10 and times to a positive 24. We have to times to a negative 24, which means they have to be opposite signs. In other words, they subtract. So we've got to look for another set that will subtract to 10. And it's this pair right here. Yeah, so you have to be very careful. It's nice because it's fast, you only have one step, but you've got to be very careful that you fit the pattern exactly. These two numbers must times to negative 24 and must add exactly to negative 10. So there's a plus 2 and a minus 12. All right, I think you're ready for a chance to do some on your own. To the boards! Here are 5 problems to give a chance to try out. Pause the video, and when you're ready to resume, go ahead and push play. All right, welcome back. Hope you had a good time with them. Here we have 1, 2, 3, 4. But don't forget, we've got to do the greatest common factor first if we can. Is there anything common between 45 and 15? Ooh, yeah, like 5s and 3s, and a 27 and a 9. Ooh, can 9 go into everything here? Nope, not into 15. But a 3 can go into everything, so we're going to pull a 3 out. What about A's and B's? Do we have A's and B's everywhere? Nope. Okay, so just a 3. So we now have 15 a squared b minus 5ab plus 9a minus 3. All right, now what's left here? 1, 2, 3, 4 terms. So we're going to be doing grouping. cut this guy in half, and we get, what can we pull out of this front half here? A 5 and an A and a B. We're left with 3A minus, if we pull out a 5AB out of this, there's only a 1 left. Now make sure you do leave that 1. It's not a 0. It's not gone, because you have to be able to distribute that back in to reconstitute what you had before. All right, bring this sign down and pull out, what can we pull out of here? 3. And we're left with 3A minus 1. Oh, sweet. Look at those. Those are the same one. Pull the 3A minus 1 out front, and it's left with the 5AB and the plus 3. And then this guy has just been sitting there the whole time, and we'll tack him on the front. And there's the solution. Now, some of you may have written 3 times 5AB plus 3 times 3a minus 1, switching those two places. That is technically called the commutative property of multiplication. You can take these two numbers, the two things in parentheses, and switch them places and have the exact same answer. Good. Number 2, 7xy plus 21x plus yt plus 3t. Do we get, is there any greatest common factor? Do we have x's everywhere? Nope. Y's? Nope. How about t's? Nope. How about numbers? Nope. So there's 4 terms. We're now going to do grouping. So chainsaw. And what can we pull out of the first half? A 7 and an x. We're left with 3y plus and we are left with y plus 3x. Nope, we took the x out. So y plus 3. All right. What about the second half? We can pull out a t. And we're left with y plus 3. Good, good. Now look, the y plus 3 is the same in both of them. Let's take it out to the right. And you can take it out either to the left or to the right. Doesn't matter. So we take out the y plus 3. And what's left is the 7x and the t. Excellent. All right, the next one. This is leading coefficient 1, so we are just breaking it up into x, and we have to find two numbers that times to 12 and add to 8. Some of you can see it right off. I'm going to write down all the factor pairs. So it's a 1 times a 12, or a 2 times a 6, or a 3 times a 4. And look, 2 times 6, those are our numbers. A positive 2 and a positive 6, and we're done. Number 4. In this case, m's are what we have. So an m here and an m here. And we have, this is a negative 12. So again, 1 and 12, 2 and 6, 3 and 4. But since it's negative, these have to be opposites. So like a negative 12 and a positive 1, or a negative 6 and a positive 2, or a negative 4 and a positive 3. Now which set adds up to a negative 1? And it's this right here, a positive 3 and a negative 4. Now if you mix those and put it as a positive 4 and a negative 3, that would be incorrect. Those would not add up to a negative 1 in the middle. All right, the next one, x squared minus 9x minus 36. So we've got a times to a minus 36. Oh, let's get our parentheses out here. So we have x and x, 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6. And again, opposite signs. So one set of these has to be negative. So I'll put it over here and see if we get these to add up to a negative 9. And there is our set right there. These guys add up to negative 5. These guys add up to 0. So it's possible that guy could be gone. And so we get a plus 3 and a minus 12. Excellent. Let's return back and learn some more. Okay, so now we reach trinomials that have leading coefficients, and we run into the issue of why these leading coefficients change it from being so nice and fast to a slower process. Let's look at a couple of examples. If we had 2x plus 3 times 4x plus 5, let's see what happens in slow motion as we multiply these. Okay, that's 8x squared plus 10x plus 12x plus 15. Ooh, so we get 8x squared plus 22x plus 15. Now, take a look at it and see why we can't just use this method. We're like, oh yeah, if you had an 8x squared, you could break it up into a 2 and a 4, and the 15 is 3 times 5. But notice where this middle term came from. It wasn't 3 plus 5 to give you an 8. And you're like, oh shoot. Yeah, these middle terms were made up of the first times this guy and the first one times this guy. So this leading coefficient meant that there are some weird things going on inside. It changes these numbers, so it's not just a 3 and a 5 anymore like back in the purple in this try fast. So we have to be very careful. So the question is, how in the world could you do it? 8x squared plus 22x plus 15. Like that. And you're like, how do we undo it? Well, in this case, this is why it's a little bit slower, is it takes a few steps to break this apart. Because just for your information, when I learned how to do it, this is how we did it. We said, oh, this could be a 2x and a 4x, or it could be an 8x and a 1x, and this could be a plus 15 and a plus 1, or it could be a plus 3 and a plus 5, or any combination of those, and we guessed and checked until we got this exact polynomial. And that was incredibly laborious. So I'm about to show you a secret that I was shown later on and found that this was like amazing ability to undo these. So let's show you how to do it. The secret is this number right here. This 22x, where did he come from? Well, he came from a 10 and a 12. So that's 8x squared. If we do plus 10x plus 12x plus 15 and break him up into his original pieces, watch what happens. We now have 1, 2, 3, 4 terms. Do we know how to deal with 4 terms? Of course we do. That's called grouping. I'm going to change to that color so you can see how powerful it is. Saw that guy right in half and you're like, oh, what can I pull out of this half right here? Well, a 2 and an x. We know how to do this. We're left with a 4x plus a 5. And over here, what can we pull out of this guy? A 3. And we're left with a 4x plus a 5. And we pull the 4x plus 5 out that way, and we're left with 2x plus 3. Multiplying that, 4x plus a 5. Indeed. Now look at what we got up with. Look at that. We undid it exactly. And some of you are thinking, you so cheated. How did you know it was a 10 and a 12? How did you know it wasn't an 8 and a 14 or a 4 and a 18 or something like that? I'm like, that is a very excellent point. So here is the grand secret. Be aware that once you find those numbers, it's just grouping. So let's teach you how to find those numbers. If you have something like 6x squared plus 17x plus 5, here's the secret. This middle number is messed up from the easy, fast way, the purple way, by this 6. That's the thing. The 6 has to be included. So what you do, you take 6 times 5, the first coefficient, the leading coefficient, a, times c. So let's write it out here. A times c. And then 6 times 5 is 30. Now, what multiplies up to 30? 1 and 30, 2 and 15, 3 and 10, 5 and 6. And now it's which set of these add to b. These are the options for where b came from. And you'll notice, hey, look, that's it right there. So these are the only two numbers that will work to cause this to factor perfectly. And that's how you do it. This is called the AC method. You take A times C. So instead of just looking at C, we're taking A times C, and we then use those numbers to split B. AC split B. So 6 times 5 is 30. 2 and 15 add up to 17. So we split this guy up into its originals. 6x squared plus 2x plus 15x plus 5. Now how many terms do we have? We have 4 terms. So let's switch colors and do our grouping again. Chop it in half. What can we pull out of the front? 2x. 3x plus 1 is left. What can we pull out of the second half? It looks like a 5. And what can we be left with there? 3x plus 1. Good. We can now take the 3x plus 1. Let's pull it out. Again, you can pull it out to the right or the left. We pull 3x plus 1 way out front, and we're left with the 2x here and the 5 there. And you can check it. Go ahead and multiply these back through. 3x times 2x is 6x squared. The middle terms would be a 15x and a 2x. That's 17x, and then plus 5. Isn't that slick? Yes. AC split B. That's the AC method, and it will work on these trinomials. Let's try a couple more. 15x squared plus 14x plus 3. Ooh, what do we get there? All right, so leading coefficient is not a 1, so we have to take 15 times 3. A times C gives us 45. Now, what multiplies to 45? 1 and 45. That means this could be a 46 and it would work. Or it could be a 3 times a 15. That's how we got here. So this could be an 18 and it would work. Or 5 times 9. So, oh, there's our 14. Are there any others? I don't think so. So right there's our 14. So we break this up into 15x squared plus 5x plus 9x plus 3. All right, we now have how many terms? 4 terms. Let's do the grouping. Cut that in half. We can pull a 5x out of the front and be left with 3x plus a 1. Pull a 3 out of the next one, and we're left with 3x plus 1. And now we can pull that 3x plus 1 out front, and we're left with 3x plus 1, 5x plus 3. Excellent. Now some of you may have a question at this point and be wondering, hey, wait a second. What if I would have put the 9 first? Is that possible? Well, so 15x squared plus 9x plus 5x. It's good to see this done. 4 terms again. Let's group and see what happens. What can we pull out of this one? Well, a 3x, and we're left with 5x plus 3. What can we pull out of this guy? Well, there's nothing really that's common between a 5 and a 3, but notice the 5x plus 3 and the 5x plus 3 are right there. So many people say, you know what? Let's pull a 1 out. Now, pulling the 1 out isn't actually necessary. You can leave it as a 5x plus 3 and 5x plus 3, and when you do this pulling out here, and you pull out the 5x plus 3, you just have to make sure that when you pull it out of here, you leave the 1. I mean, you're undistributing, so you can't just leave a 0 there. And notice what we have. One of them had the 3x plus 1 in both places, and the 5x plus 3 separated, and the other one had the 5x plus 3 in both places, and 3x plus 1 separated. So it actually doesn't make any difference if you switch those around at all. Let's show you one more example and let you on your own. And here we go, 10x squared minus 13x minus 3. So we have a leading coefficient that is larger than 1 or isn't 1, and so we've got to take a times c gives us a negative 30. This is the number that we must multiply to in order to find what will split this negative 13. So that's a 1 and a 30, 2 and a 15, 3 and a 10, and many of you will stop right there and say, hey, look, we found it. Stop, 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 stop. 3 and a 10 add to 13. Yeah, we need a little bit more work here to double check that. Pay attention to the signs. Here, it would have to be a negative 3 and a negative 10 to make a negative 13. Does negative 3 times negative 10 equal a negative 30? It does not. Those are not the right numbers. All right, so in order to be a negative, we have to have something like a negative 2 and a positive 15. Ooh, but that's backwards. That adds to a positive 13. Let's Undo those and do a negative 15 and a positive 2. Is that correct? And double check it. Positive 2 times negative 15 is indeed a negative 30 and does indeed add to negative 13. That is good. So that's what we split it up. It is now 10x squared plus 2x minus 15x minus 3. And we have 4 terms. We can group. Chainsaw, we are pulling a 2x out, and we get a 5x plus 1. And here, be sure to pull this sign out, and it looks like we can take a 3 out. Yeah, that'll leave us with a 5. Good. 5x plus 1. Make sure the sign is correct. When you distribute this back in, that negative goes to both of them. So pulling it out pulls out both negative signs. And you have a 5x plus 1 that you can pull out now. Big pull out, and we're left with a 2x minus 3. Shazam! Okay, give some a try. And one more. 49x squared minus 56x plus 16. All right, so 49 times 16. That's a big number. Better pull out that calculator and punch that guy in. 49 times 16. Enter. 784. All right, let's write it down. 1 times 784. 2 times, that looks like 392. Does 3 go into it? Nope. Does 4 go into it? Yeah, 4 will go into it. Looks like 196. Is that true? Good. Okay, so 5, 6. What about 7? 7 is a little tougher. It looks like 112. 8. 8 will go into it 98 times. 9, no. 10, no. 11, no. 12, 13, 14 is twice 7, so 14 times looks like 56. Now let's try 16. Oh yeah, 16 times 49. We got that one. The next one, maybe not 21. Anything else up there? Looks like we could double 14 and get 28 and 28. Do any of those add to a negative 56? And yes, indeed, these guys do right here. Negative 28, negative 28. That was a tough one. Negative 28x. Who would give us those big of numbers? 49x squared. All right, let's chop that in half. We're doing grouping now. So, what can we pull out of this? A 7x, and we're left with 7x minus 4. And over here, we pull out a minus 4, and we're left with 7x minus 4. And we get, hey, look at this. We're going to pull out a 7x minus 4, and we're left with 7x minus 4. That's the same thing. We could write that down as 7x minus 4 all together squared. Now, I kind of set you guys up here. We're actually going to show you this guy right here as one of the special cases that might be able to save you a lot of work. So let's see what we're talking about. Perfect squares. When you take a number and perfectly square it, you'll notice this right here is 4 times 4, and that's 7 times 7. I'm going to take a moment and write down the perfect squares. 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, and you could keep going and get a whole bunch more of these, and it keeps on going forever. But these are really special numbers. If they end up being here, you might get a special case, a shortcut. Let's show you what the shortcut looks like. If I were to take something like x plus 7 times x plus 7, notice just based on this rule up here, this shortcut that we did, we get x squared plus 14x plus 49. These guys are the same, so this guy is just double of what is in there. Same thing if we had, say, 2x plus 3 times 2x plus 3, a perfect square. Watch what happens in the slow motion. We get 4x squared plus 6x plus 6x plus a 9. So this is 4x squared plus 12x plus 9. Now I'm going to write this up here as 2x plus 3 altogether squared. Remember, no freshman's dream, no jumping that squared in through the plus sign. But right here you have a perfect square. This number is a perfect square. See, 9 is a perfect square. And this guy ends up being 2 times 3 doubled because the middle terms are exactly the same. Let's watch it one more time. 5x, let's do like plus 11. Let's do a minus 11. Yeah, that'll show you everything that's going on. 5x minus 11, perfectly squared. So we'll write it out again to multiply it out correctly. We get 25x squared minus 55x minus 55x. See how they're always the same in the middle? So they're just, it's 11 times 5 doubled is what we're going to end up with, and then plus 121. So we get 25x squared minus 110x plus 121. So this right here, notice 25, perfect square. It's right there. 121 is 11 times 11. It's on this special list of numbers. So you really need to know this special list of numbers to pick out these special cases. 121, and then if it's a 5 and an 11, 5 times 11 doubled is indeed 110. So what this does, it would allow you to do some of these, again, they're called special cases, in a very quick manner. You'd be able to take 49, you're like, hey, that's 7 times 7. And 16 is 4 times 4. And write this down as an answer without doing all of this work. And just check. 7 times a negative 4 is negative 28. Doubled is negative 56. Done. You don't have to do very much work. Let's show you one more of those to make sure you can identify those when you come across them. Here we have one, 36x squared minus 156x plus 169. If you look at this and you're like, oh, yep, we're going to have to take a times c and split b. Oh, 36 times 169. As soon as you hear that, oh, sometimes you'll have to do it. But if you can identify this number, 36, is one of these special perfect squares, there it is. 169 is one of these perfect squares, there he is. Then this is 6 times 6, 13 times 13. Let's check to see if this will work. It's kind of a shot in the dark, but let's see if it works. And a 13. This will give 36x squared. Is 6 times 13 doubled? 156. It's a negative, so this better be a negative. 6 times negative 13 is negative 78. Doubled is 156. Ta-da! There's your answer. You do not need to go through and show work on here on perfect squares if you can identify them. So that will save you a lot of work if A and C happen to be perfect squares and B is exactly 2 times A times C. So if A is a perfect square and C is a perfect square, and this is 2 of the square root of that one and the square root of that one. Alrighty. Now you can give it a try. To the boards! Here's the problems. Go ahead and write them down, give them a try, pause the video, and resume when you're ready to check your answers and see how you did. Welcome back. Let's give it a shot. Here we have number 1. 8x squared minus 63x minus 8. Are they perfect squares? They are not. So we need to do the AC method. 8 times negative 8 is a negative 64. What are the options here? 1 and 64, 2 and 32, 3, 4, and 16, 6, 7, 8, and 8. All right, so looks like a 1 and a 64 with a negative on the 64 and a plus on the 1 will give us a negative 63. So we write down 8x squared plus x minus 64x minus 8. And we now have 4 terms, so chop it in half. What can we pull out of the front half? X. We're left with 8x plus a 1. What about this second half? We can pull out the negative sign, and it looks like an 8, and we're left with 8x plus 1. And so taking the 8x plus 1 out of both sections, we're left with x minus 8 times 8x plus 1. And yes, that can be written with the 8x plus 1 out on the left as well. Number 2, 5x squared minus 19x plus 12. Is this a perfect square here? It is not. So we'll have to do a times c is 60. 1 and 60, 2 and 30, 3 and 20, 4 and 15. Oh, that looks like that'll be our 19 right there, but let's keep going. 5 and 12, and 6 and 10. And yes, but they do add up to a negative, so you got to have 2 negatives in there. Do they still times to a positive 60? They do indeed. So those are our numbers, 5x squared minus 4x minus 15x plus 12. And what can we pull out of this first half? An x, and we're left with 5x minus 4. And what can we pull out of this second half? Got to pull out that negative sign, and it looks like a 3. Yeah, we're left with 5x. We pulled out a negative 3, so that is indeed a minus 4. And those two, look at that. Isn't that heartwarming to see them come out the same thing? So you can pull out that 5x minus 4. Let's pull it out this way. We're left with x minus 3 times 5x minus 4. And if you'd like to check it, go ahead and multiply that back out, and you'll get exactly that. All right, number 3. Yeah, 3 and 6, not a perfect square, so we'll have to do a times c is a negative 18. And then 1 and 18, 2 and 9. Oh, that looks like that'll give us a 7. 3 and 6. But which one's negative and which one's positive? It would have to be a negative 9 and a positive 2. Now double check. Does that times to negative 18 and add to negative 7? Indeed. So we got 3x squared plus 2x minus 9x minus 6. We now have 4 terms. Chainsaw. Take the x out. We've got a 3x plus 2. And here, take the negative. 9 and a 6 is a 3. We get 3x plus 2. Indeed. 3x plus 2. Same in both places. Let's take it out front. And we get 3x plus 2 times x minus 3. Excellent. All right, number 4. 121 times 16. Ugh, that seems so horrible. Well, it is. It'd be a huge number, and eventually you get a 44 times a 44 will give you the same number. This is a perfect square. That's a perfect square. So we're going to take a shot in the dark at 11x and a 4 being a perfect square. And this is a minus sign, so let's double check. 11 times 11 is 121. 4 times 4 is 16. But 11 times 4 is 44. Doubled is 88. So we are done. That's it. Just one step on those special cases. That's nice. All right, what about this one? 144 times 49. No, let's check. Do you see that special number? It's a perfect square and a perfect square. Looks like it's going to be a 12x and a 7. All right, and there's a plus sign in the middle. 12 times 7 doubled. Is that 168? 12 times 7 is 84. Doubled is indeed 168. We are done. We don't even have to do it. You could actually do this. 144 times 49. And yeah, you get up there something like 1,300 and 99, I don't know, something up there really big. Turns out it's going to be 84 times 84. Amazing. And that would be the middle terms that would split it. But yep, that's it. Those are special cases, perfect squares. Nice job. Let's move on to the last few. All right, so we actually took care of the perfect square special case as kind of an addendum to this one, or how to get out of this one if A and C are perfect squares. So let's talk about this one, the difference of squares. Well, over here, again, we're working with these special sets of numbers, but there was a special pattern that came up when you had two things that were almost exactly the same, multiplying together. The only difference was the sign in the middle. When you did this, there was some magic that occurred. X squared minus 3x plus 3x minus a 9. Notice what happens to these middle terms. Instead of doubling together, they're opposite signs, so they went away and you were left with two terms. That's important. This is two terms right here. And you ended up with a subtraction sign in the middle between a perfect square and a perfect square. Let's try another one. If we had 5x minus 7y and a 5x plus a 7y, they end up being 25x squared plus 35xy minus 35xy minus 49y squared. And what happens to the middle terms? They add to 0. They're exactly the same but opposites of each other. 25x squared minus 49y squared. Now you should note that you will always, if you eliminate these middle terms, you will always end up with a minus sign in between there. So you'll notice this phrase right here, difference of squares. When you are going to factor, you need a minus sign in order to follow this pattern. So let's do a couple of them, see how they work. 16x squared minus 121. Well, this is 4 times 4, and that's 11 times 11. So it was a 4x and an 11 and a 4x and an 11. One of them had to be positive and one of them had to be negative in order for the middle terms to cancel out when they multiplied. These guys, they're not the same thing. We can't shortcut like we did here with a perfect square and write it as 4x plus 11 squared. It's a different pattern. These guys actually have names. They're called conjugates. Okay, conjugates, kind of partners. They're the same but different, but they work together to produce only perfect squares when they get done. All the non-perfect squares cancel out. Let's do another one. 81x squared minus 1. Is 1 on that list? Yes, it is. 1 is a perfect square. This is 9x plus 1 and 9x minus 1. Yeah, 9 times 9 is 81. 1 times 1 is 1. Good. What about 100x squared minus 169? That's on the list right there. So yeah, this would be 10x minus 13, 10x plus 13. Oh, look at that. That's sweet. Hey, and you will see this often come up, x squared plus 9. And you may be tempted to try to factor this. Many of you will do, oh, x plus 3, x minus 3. Ah, you forgot the rule. You will always, if the middle terms canceled, which in this case somehow they did, you'll always end up with a minus sign. So that guy won't work because positive 3 times negative 3 is a negative 9. So that guy doesn't work for that. And you're like, oh, make it x plus 3 times x plus 3. No, this is the perfect square. This gives you x squared plus 6x, right? A 3x and a 3x in the middle, plus 9. That one doesn't work to factor it. And you're like, oh, we'll make them both negative. That actually didn't help at all, because this right here would make a negative 6x in the middle. Yeah, in order to cancel the middle terms, you need opposites of each other in the middle. So that middle sign, you have to have conjugates. So in order to cancel out the middle terms, this has to be a minus. So this guy, it is very well known as the sum of squares, meaning plus instead of minus, sum of squares, and it is prime, meaning it cannot be factored using the real numbers. So we can't do it. So if you see that, your answer is that's a prime polynomial. It can't go down. But if it has a minus in it, you'll be able to take it down. Excellent. Now let's move on to the sum and difference of cubes. Some magic that you may have missed, you're going to see now. Let's do x minus 3 and then use some of these numbers in x squared plus 3x plus 9. And we're going to see some magic happen. It's kind of cool to watch it from the forward direction in multiplication before we go back and see how to undo it. So let's multiply these out and we get x cubed plus 3x squared plus 9x. Okay, that's what happens when you jump the x through. Now let's jump the negative 3 through. That's negative 3x squared minus 9x and minus 27. Oh, look at that. We end up with x cubed minus 27. Now notice this was 3 squared, and we got a lot of 3's going on. 3 times 3 squared, 27. This is actually 3 cubed. Ah, very interesting. So we're going to need a whole new list of numbers eventually here, the cubes. But let's see what happened. Do you see how that guy went away and that guy went away and it was just minus 27? It canceled 4 middle terms and left a binomial times a trinomial, 6 terms, left it with only 2 terms. So we're going to be down here again. This special case, you're going to start out with only 2 terms and go backwards and see how you can create where it came from. Let's do another one like that. X minus 5 times x squared plus 5x plus 25. Do you start to get a feel for what the pattern is? Well, let's multiply it. So we get x cubed plus 5x squared plus 25x. That's multiplying the x through. And then on the other side, this minus sign gives us a minus 5x squared. And minus 5 times 5 is a minus 25x. So that was crucial to have that number here, and it's squared here. And then at the very end, 5 times 25 is minus 125. And so we get x cubed, that guy and that guy, and that guy and that guy, and we just get minus 125. Look at that magic. So let's articulate what the pattern is. If we were to take this and write a minus b, just like that, that's the key. You have this guy squared here, so that times that will give you the cubed. Then notice that this plus sign and this minus sign are what cancel everything out in the middle. So that's plus whatever these two numbers are times together. And then on the end, you have the plus b squared. And when you multiply these out, you will get a cubed. Everything in the middle will cancel, minus b cubed. So this is how you go backwards. If you have something that is a difference of cubes, it's going to break up into a minus b, a squared plus ab plus b squared. This looks very close to a perfect square trinomial, this special case right here, but it is not because it does not have a 2. So usually this guy doesn't factor out. But this, if you see a difference of cubes, is how you will break it up. So let's identify some cubes. The perfect cubes are 1 cubed, 2 cubed, 3 cubed, 4 cubed is 4 times 4 is 16 times 4. Yeah, that's 8 squared is also 4 cubed. 5 times 5 times 5. 6 times 6 times 6. 7 times 7 times 7. 8 times 8 times 8. 9 times 9 times 9, and of course 10 times 10 times 10. And that's usually as high as you need to go as far as memorizing cubes, but it might not be a bad idea to recognize those numbers when they show up. I'll show you what I mean. If you have something like 27x cubed minus 512, yuck. It's doable though. This is 3x. Perfectly cubed, and this guy is 8 perfectly cubed. So to factor them is 3x minus 8 and 9x squared plus, this times this is 24x, and then plus 8 squared plus 64. And as surprising as that is, when you multiply these guys out, all of the middle terms will cancel, and it will be left with 27x cubed minus 512. Fascinating. Difference of cubes. Now, what's even more surprising is what happens when there's a plus sign in here. Is that even possible? Because we have more terms in these factors that go to the difference of cubes, it turns out, yes, you can make that a plus sign and this a minus sign, and it will work. So the sum of cubes formula actually looks like the following. If you have a cubed plus b cubed, it's going to be a plus b, then a squared, ab, and plus b squared. And the way I remember it is once you know that this is the same, so notice how these two signs match like that. Yeah, these two signs match. That a times a squared gives you the a cubed, and the b times the b squared gives you the b cubed. And all you have to do is remember one thing, and that is that in the middle, the key that cancels everything out is when this is an opposite sign. So if you're a minus there, that's a plus. If you're a plus there, that's a minus. And then it's just whatever this guy is times whatever that guy is, AB. So there's a cute little jingle that people memorize this with. I'm not so sure it's valuable, but other people use it, so I'll try to sing it the best I can. It goes to Jingle Bells. So first times first is first, last times last is last, first times last is middle. Isn't this a blast? First signs from the problem. Second is its reverse. Last sign's always positive, no matter what the first. Oh, sum of cubes, difference of cubes, isn't this a blast? And something, something until we get the problems done. I don't remember what it is. I guess I'll have to sing it for you later and put the words up. So that's the formula, or those two are the formulas that will allow you to do both a sum and a difference of cubes. Notice the sum of squares is distinctly missing from those that are factoring. Okay, give some of them a try on your own. To the boards! Here are some problems for you to write down and try on your own. Go ahead and press pause, write them all down, and then try them. When you're ready to move on and check your answers, go ahead and push play again and we'll catch you back up. Welcome back. All right, let's do it. We got quite a few of them here. They've broken them up into some different formulas that we'll be able to use. So on this one, don't forget, most important, you got to take out a greatest common factor first. So in this case, we can take out a 6x, and we're left with 9x squared minus 1. What's left here has two terms, which is a difference of squares. There's a special number. So this guy breaks up into 3x minus 1 and 3x plus 1. And the 6x stays out in front. So it looks like that. Excellent. Number 2, this has two terms, but wait a second, the minus sign's there. Should look like 64 and a minus x squared. Or if you wanted to, you could have actually pulled out a negative 1 and wrote it as x squared minus 64. Either one of those would have been okay. But this is now a difference of perfect squares. So we get 8 minus x and 8 plus x. Of course, if you had done this one up here, it's x minus 8, x plus 8 with a negative 1 out in front. And either one of those are okay and correct factorings. Number 3, we have two terms. There's a subtraction in the middle. So this is 11 perfectly squared, and that's 5z. So we have an 11 and a 5z, minus and a plus. And again, you could have done what you did over here and take a negative 1 out and had the z's come first and put it in descending order if that's your preference. Excellent. So that used our differences of squares. All right, let's look at the next one. This is two terms, but this is a difference. That's not a perfect square, and that is 5 cubed. So we've got an x and a 5 that we're working at. And so we've got x minus 5 here. Now let's do the other one. X times x squared would give us x cubed, and negative 5 times a positive 5 squared, 25, gives us that one. So we're using this formula right here. And then in the middle, we're going to have a plus x times 5, so plus 5x. And yes, that works indeed. So let's try it again with this one. Is 27 a perfect cube? Yep, it is a 3x, which gets cubed here. And this guy is a 7. So Once you have identified those, you can use your cute little jingle if you like it. First times first is first, so that's a 9x squared. Last times last, 7 squared, is that one. First times last is middle, so that's 21x. Excellent. Then first signs from the problem, the second's its reverse. So these two have to be the opposites. And yes, again, we're using this problem, this a cubed minus b cubed right up here. And then that one's always positive. There we go. And you can double check that and see if it works out. Good. Ooh, what is this one? This one has 4 terms. I wonder what we're doing with this guy. So with this, we've got 4 terms, and it is, let's write it in the right way, x cubed minus 2x squared. Sorry, not the right way, descending order, as that will make it easier to see what's going on. 5x minus 2. All righty. There's not a common factor. This is back to grouping, I guess. Taking x squared out here, and we're left with x minus 2. And can't take anything out. So we've just got plus 1, 5x minus 2. And those are not the same. This guy is prime. They threw in a prime one. What was up with that? All right, let's keep going on with what we've got here. This one, t cubed minus 64. Is this a perfect... Wait, 64 is a perfect square, but it's also a perfect cube. Yeah, this is t minus 4. T cubed minus 4 cubed is what we have here. So we're going to be using this formula again. So we've got a t squared, and we've got to have a plus 16 over here, and then a 4t in the middle, and it's got to be a positive. Okay, so that used that formula. We had t minus 4, and then t squared plus 4t plus 16. Good. A cubed plus 8. This is a sum of perfect cubes. So we are going to be using this formula now, which is a plus 2 times 2. That's 2 cubed. So we're using this formula. So we have a squared minus 2 times a plus a 4. That's that formula right there. All right, 9. Ooh, this is a plus sign. This looks like we're going to be at perfect cubes. 729 is 9 cubed, and this is 10 cubed. So yeah, our numbers that we're going to be working with, our a's and our b's, are our 9q and a 10. And it's a plus sign, so we are at this formula right here. So 9q plus 10 is what we're going to start with. And then we get a squared, which is 81. Oh, q squared minus a times b, so minus 90q, and then plus 100 plus that b squared. There you go. There you have it. Good.